Welcome. To understand the breakthrough behind the Vision Transformer, or ViT, we first need to look at the divide that existed in deep learning. On the left, we have natural language processing. For years now, the transformer architecture has been the undisputed king here. Transformers treat data as sequences, discrete tokens like words flowing into a mechanism that can attend to the entire context at once. It's global, and it's powerful. But on the right, in computer vision, things have been different. Images aren't just sequences, they are 2D grids of pixels. Here, convolutional neural networks, or CNN, have dominated. They rely on a sliding window approach. This yellow box represents a convolution kernel. It scans the image locally, looking for features step by step. This assumes that pixels are only related to their immediate neighbors, a concept we call inductive bias. For a long time, we believed this spatial bias was essential for vision tasks. We thought transformers were too general to handle pixels efficiently. But the authors of this paper asked a radical question. If transformers are so powerful, can we strip away the convolutions and solve computer vision using a pure transformer? Building on the overview of the architecture, let's look closely at the very first step. How do we actually feed an image into a transformer? Standard transformers are designed for sequences like words in a sentence. But an image, X, is a 2D grid of pixels. To bridge this gap, the Vision Transformer treats the image not as a single object, but as a collection of sub-images. We split the image into fixed-size patches. In the paper, these are 16 by 16 pixels. Here, we visualize them as a 3 by 3 grid for clarity. Notice the order. We read the image from top left to bottom right, creating a linear sequence. Now we have a sequence, but each element is still a 2D patch of pixels. The transformer needs vectors. We flatten each patch and map it to a vector using a trainable linear projection. You can think of this process as translating raw visual data into visual words or embeddings that the model can process. This resulting sequence of vectors is now ready to enter the transformer encoder, almost exactly like a sequence of text embeddings in NLP. Here we have our sequence of linear patch embeddings from the previous step. But before we feed this into the model, we need to make two crucial additions. First, we prepend a special, learnable vector to the sequence, known as the class token. Just like in BERT for NLP, this token's job is to aggregate information from the entire image to represent the final classification state. Second, remember that the transformer architecture is permutation invariant. It has no inherent idea of left, right, up, or down. To fix this, we add learnable position embeddings to every vector. These are added element-wise to our patches, injecting spatial information directly into the data so the model knows where each patch belongs. Now, the sequence is ready. We feed this combined sequence into the transformer encoder. This massive block consists of alternating layers of multi-head self-attention and MLP blocks, allowing every patch to attend to every other patch. Finally, for the image classification task, we don't look at the output of every patch. We focus specifically on the output state of the class token. This vector, now rich with global image context, is passed into a final MLP head, which outputs the probability distribution for our classes, correctly identifying this image as a bird.
To understand why ViT works, we must understand the trade-off between structure and scale. This is the battle of inductive bias. On the left, we have the convolutional network. It comes with strong, built-in assumptions. It assumes locality, that pixels are related to their neighbors, and translation equivariance. This is high inductive bias. It's like giving the model a rulebook before it starts learning. On the right, the Vision Transformer. It treats the image as a sequence of patches with global context. It has much less inductive bias. It doesn't assume structure. It has to learn it from scratch. Now, let's weigh them against each other. In the small data regime, like ImageNet-1K, the CNN has a head start. Because it already knows about locality, it learns efficient patterns quickly. The transformer, lacking these rules, struggles to generalize and overfits. Here, bias is a benefit, but look what happens when we increase the scale. When trained on massive datasets, like JFT300M, the picture changes completely. The CNN's rigid rules now become limitations. The transformer, free from these constraints, learns more flexible and powerful patterns directly from the raw data. As the authors state, large-scale trumps inductive bias.
To truly understand the impact of the vision transformer, we have to look at how it scales compared to the champions of the previous era, convolutional neural networks, specifically the big transfer, or BiT, ResNet models. Let's visualize this relationship. On the x-axis, we have the size of the pre-training dataset, ranging from the standard image net with 1 million images up to the massive internal JFT dataset with 300 million images. On the y-axis, we have transfer accuracy. First, let's look at the ResNet performance, shown here in blue. Notice how it starts relatively high. This is due to its inductive bias, the built-in knowledge about how images work, like translation invariance. However, notice how the curve flattens out. As we feed it massive amounts of data, it saturates. Its rigid structure eventually limits its ability to learn more. Now, let's trace the vision transformer, or ViT, in red. On smaller datasets, it actually performs worse than the ResNet. Without those built-in inductive biases, it struggles to generalize from limited data. But look at the trajectory. Because it makes fewer assumptions, it is more flexible. On the left, inductive bias is king. The CNN wins. But as we move to the right, to the scale of 300 million images, we see the crossover. The ViT curve keeps rising, overtaking the ResNet. This graph illustrates the paper's core discovery. With enough data, large-scale training trumps inductive bias. ViT doesn't just catch up, it establishes a new state-of-the-art.